Hello, and welcome back to Unconventional Computing CS492A in fall 2024. Our topic today is unconventional problems, and this topic will be presented by Elcin. So I'm going to switch the focus to Elcin, who will first introduce himself and then start with a presentation.
Hello everyone, my name is Elcin. I am studying computer science and maths, and my main focus is studying AI, and also today's topic is unconventional computing problems, which is closely related to my interests. Let's start to the presentation. Okay, now the topic is unconventional computational problems. The table of contents includes introduction, CPU versus GPU, constraint computations, theorem on universal computers, quantum versus conventional computers, future directions, and reference. Now, what are the limits of the computation today, or what are the types of the computation? I can talk about the quantum computing scheme or biological cell computing. You can see that in the algorithmic part, you can implement it in electronic way. Also, you can visualize it in cellular implementation. Outputs of it is calculated by several computations. Also, simulating certain problems with parallel computing can be done by end processors in the CPU or GPU, or you can also do parallel computations on, again, biological cell computing, as well as you can re-implement it in quantum computation. However, our main concern is finite steps and universality constraints, that you can put several inputs and outputs and put some constraints that can be closely decisive in the time complexity and the sequential orders of the outputs. Now, let's start with our main concern, the processors, or the main idea that it comes from. The processors gets some input as integer operand, some integer operand inputs and status, opcodes references, and it outputs some status and integer result. This is an example of simple ALU, and this happens in the CPU, or you can also put GPU here. And now, the parallel processing is quite important in some computations for this issue, because we are dealing with a lot of inputs from different hardwares and stuff. Then, a CPU is more stable example of computing, and you can also see the GPUs for being optimized for some computations like matrix multiplication and other stuff. Now, here is the video about CPU versus GPU that you can easily understand what can be the difference between them. The main reason I put this video on is because
In this video, we're going to compare
it explained the idea of sequential and the parallel processing that we are going to talk about it later. Now, what are constraint computations? Computations must satisfy a mathematical property, and the well-known example of it is the sorting algorithms that you can see. There are many different ideas about it, but none of them gives us the complexity of one solutions, at least like something related to n. And now the idea starts from here that if you are given an element set, you can't actually, if it is randomized, you can't actually sort it in less than some amount of steps. And we have put the constraints here to better understand. And you can see that, well, if we have m, if we can do m steps in one time unit, and if n is quite large than n, you can't do it in the designed time frame. Now, the other problematic examples of solving computing can be related to inverting a non-singular matrix. without ever dividing by 0, finding shortest path, and stable sorting that can lead to some problems throughout the algorithmic solutions. Now, what are the computational complexities in this example, or we are going to talk about to consider while we are thinking about it? So, like you can see the list here, time varying computational complexity and rank varying, and we'll talk about the global variable paradigm. What's rank varying computational complexity? When we have several states, and some states are more important than the other ones, and depending on this one, if we have high complexity, then higher ranked stage will take a lot of steps for us. And because of this, the higher ranks have a lot of disadvantages. They might be the prosecution of this stage can be postponed a lot for this reason. And applications, you can see that the stage execution order impacts resource requirement or accuracy. Like one example coming to my mind is like training machine learning models. Like the order of the pictures can be dislocated to make a video that you can obviously see the malfunction in that scenario. The time varying variables, like we know that some operations are depending on the time and input, maybe from the hardwares, and the time dependent variables has to be calculated as fxit at specific time t. But sometimes the input cannot be calculated in some time interval because some other thing is calculated in that time. Therefore, parallel processing is quite crucial in this issue. And the interacting variables, like if you have any variables, like one change in one of the variables can immediately affect all the variables. Maybe like if we have the relation of ordering, if we change one of the elements order, we can see that this relation changes entirely for the set. Like something like only one change can create a domino effect, and that's why the complexity can go up. And sequential computation issues comes here that yeah, the same reason this can be quite uncontrollable. And parallel computation is solution here with M processor. You can consider each of the variables here. And uncertain time constraint is another topic here is as well, like we have input calculation and output. The deadlines are unknown, like you don't put any deadline to calculate it. Maybe like if you see that time clock, you can from in your computer, you have the deadline that at exactly 2:44, you have to show 2:44 for the computer. But this uncertain time constraints doesn't use such thing. But we don't know exactly about it. But you can. But you have to memorize. You have to make the computer to memorize this function as well. Now the global variable paradigm comes handy here. We have P0 and P1 to process, and we have only X, a global variable, which is used in two different processes. And it can be like, again, something related to clock or some global variable. Yeah. Now what is the scenario? Let's look at P0 and P1. P0 checks if X is 0. P0 always checks if X is 0. And P1 also checks if X is 0. Then the if statement says that do one addition to the X, else loop forever. Same thing, like just take Y another variable and add Y to the X, or loop forever. Because of this reason, we can look at single processor case and two processor case. Single processor, what does single processor do? Let's say it is doing a sequential computing, P0 comes first, and for this case, P0 makes X1, and then P1 can check if X is 0. Therefore, it goes into an infinite loop. Therefore, we can't, there is an error. Halting problem. Yeah, that's why we can say that it can't execute it sequentially without an error. But for the two processor one, in the beginning, both P0 and P1 assures that X is 0, and they both add 1 and Y. Therefore, X becomes Y plus 1, and without an error, the code ends, or the running ends. Now, key observations on sequential execution is that, like, limitations of these executions are you can, while executing one process, you will stop considering the global variables and global interactions between variables. And for the illegitimate simulation, you might reset X to 0 to start again for the execution. Therefore, we have to consider where to do the sequential execution and where not to do. Now, for this case, P0 and P1 should be executed simultaneously, and they can work independently. However, we have to make sure that X is updated correctly. Now, there can be also some consideration about time issue, that some variables depends on the time. And therefore, if we have less parallel processors than the actual functions, we might end up in wrong result. Maybe like if we have to do n plus 3 process, but we have n processors, then like additional 3 processors will not be executed in exact time. That should be done, but it is not going to happen. Therefore, it becomes an error for us, or a problem. Now, as I said, we can generalize the number of the process to make it P0, P1, and Pi, and P up to Pn. And you can see that we can add 0, Y0, Y1, Yi minus 1 to this sequence. And we can also say that if we have like n over 2 processors, we might not deal with the n processes. Yeah. Now, for this case, everything is initialized to 0. Local variables also are initialized to 0, and also to mention that y0 up to yn minus 1 are set to 0 before, are set to be local variables, that the changes on them might not affect our final result. And what is the behavior of the process? Each process takes and updates its respective global variable. And if the variable is 0, it executes the respective action, and otherwise the process enters an infinite loop. Okay, now, what are the limitations of sequential execution? Well, we know about the supertask machine or accelerated machine, but also the Turing machine as well. The infinite number of algorithm steps per time unit is not possible. Therefore, we will fail to perform the required computations for the sequential execution. And the same reasons, again, no parallelism leads to this result. The need for parallel execution comes handy when simultaneous execution gets handled. Yeah, exactly the same observations again. Each computational problem can be solved on a computer capable of executing an algorithmic steps. However, failure with fewer steps will result in the errors and other limitations. Also, the additional thing I want to talk about is the dynamic problem size. The problem size can change in some cases, like we can sequentially add the input or non-stoppably add the input to the equation, and after a time we can, okay, let's say we have x and y, and we at the end we add some brackets and divide some orders changes, and we can't put everything in the process at the same time. Therefore, like if some input is included, you can't directly process it with several amount of processors. That you have to wait a little bit to make sure that every computation is correct, then go back to computing again. Also, our main takeaway is no universal computer exists in this real, because in algorithmic steps, we can't put infinite number of algorithmic steps per time unit. Or in case that if you can put infinite amount of algorithmic steps per time unit, there can be also other issues, other problems that you might not get. You might not get the exact solution for each sequential input data. Yeah. Yeah, for the Turing machine, random access machine, Turing machines, you can say that Turing machines assumes that you have infinite amount of, how to say, infinite amount of data and operations throughout the time. But at some time intervals, you have only finite condition. But yeah, exactly the same stuff I've talked before. Yeah, the thing I've talked before, like Turing machine assume unbounded time and space for computation, but this doesn't affect the real world computing limits. The accelerating machines increase their speed every time step, but cannot be universal if we have the bound for the acceleration itself. Now, the concept of universal computer, our takeaway is it should have infinite number of algorithmic steps per time unit. Now, quantum computing can be quite related to the universal computers if we can find additional algorithms, which are impossible on classical computers, even those with infinite resources. Quantum computers use qubits that can exist in multiple states simultaneously, and which is quite different than the idea of the conventional computers. Qubits represent both zeros and one at once, and that they are connected to each other, enabling faster processing. However, again, this can't make sure that we can do infinite number of steps in one time unit. Exactly. Now, what are the future directions? To address the computational challenges, we have to address the problems like time varying variable paradigm and close time like curves. I don't know why you need to here. Okay, limitations. Again, this mathematical constraints is the limitation here. Okay, now the conclusion part. Unconventional problems demand new approaches. We take it away, and we have limitations of sequential processing, and we need parallel processing, but I don't know. We are not sure if we can solve the universality problem. And this is the result of this topic, that we are quite pessimistic about finding universality in this conventional and unconventional computers. The references are here. Thank you for listening. Yeah, that's all.
So, yes, thank you very much. And now, as usual, we're going to take a short break to let students, participants digest it, and then we proceed to the Q&A session, where participants are encouraged to ask some questions. And if you know the answer, then it's good. If you don't know the answer, feel free to speculate. Just say whether you're speculating or whether you're giving the answer. Okay? So short break now, might be like 5 minutes. Okay, here we are back online, ready for the Q&A session. And now I'm going to enable all students, all participants to unmute themselves and to start video. And please use that opportunity to ask questions to Elcin. Maybe previous speakers had arranged with some participants for a specific question to ask. Not this time. I want to ask a question. Maybe the conclusion, the takeaway message from your presentation, from your chapter of this book, was that there exists no universal computer. On the other hand, we know from computability theory that there exists a universal Turing machine. That was one of the big contributions of Alan Turing, to construct a universal Turing machine that can simulate any other Turing machine. So there is a discrepancy, right? On the one hand, there is a universal Turing machine. On the other hand, this book chapter and your presentation conclude that there is no universal computer. How can we resolve that seeming discrepancy?
Can you explain me what do you mean by universal Turing machine? I don't have exact idea about it. I have to search for it.
Right. So a universal Turing machine is one that can simulate any other Turing machine. It's like a interpreter, which can interpret or simulate any other machine. Like you can simulate Windows on a Macintosh computer, and you can simulate Intel processors on a Acorn ARM processor. So
okay, now I got it. Yeah, the universal, one of the conditions that I forgot to say was that if we create a universal computer, this computer should process everything that the finite conventional computers can process. These has similar properties or constraints for the universal computers and universal Turing machines. But the universal Turing machine says that you can process any other Turing machine. But this doesn't convey the meaning of infinite number of steps, because like what I understand, like you have the integer numbers in m1 to mn. This has the LCM that is divisible by each of them. Like this still doesn't mean that it is infinite, but it is finite at least. But our universal computer should calculate infinite number of steps in literal one time unit. Therefore, like we say that complexity is quite ambiguous in this term. That's why, like, the universal computer, the thing that I talked about the universal computer is quite perfect in abstract, that can calculate everything. Not only the infinite condition holds for it, but also like the order, sequentiality, and parallelism, and the correctness of output, and also the like. What's my idea is like there are countable and uncountable infinities, and what happens with that in the universal computer is also ambiguous. Therefore, the definition of universal Turing machine is well defined, but the thing, the universal computer is not defined. That's why I can't compare them.
I understand. That's a good explanation. Thank you so much for this explanation.